back, everyone. This should probably be one of the most important videos for this unit, so make sure you pay attention for this video. We'll be talking about para, ortho, meta, and directing roles, essentially where a substituent or a reagent should go if I already have a pre-existing substituent, or whether that's one or two. So we'll cover all different scenarios about that. We will also talk about half of Chapter 17, electrophilic aromatic substitution mechanisms, and all of those aromatic reactions. And then in the next video, we'll talk about the remaining part of Chapter 17. Alright, so let's dive into it. Okay. So here is an example of a benzene ring, because that's all about aromatic reactions, and a benzene ring is aromatic, so we'll use that as an example. Okay, so here I have my X, which is just some type of substituent, and that substituent is either going to be electron donating or electron withdrawing. That's what EDG and EWG stands for. Now that substituent, across from it is the para position. On the sides, it's going to be my ortho position. And then 2 carbons away are going to be my meta position. Okay? So these are the different positions you should be aware of to keep in mind as you go along. Okay? Now let's talk about some key terms. So we're going to use the word activator and deactivator a lot in this chapter. Essentially what that means is an activating group is known as electron donating group, and a deactivating group is known as electron withdrawing group. Now the reason why these are called electron donating and electron withdrawing, or activating or deactivating, is, so let's take a look at these two examples. So this is an activator and this is a deactivator. Okay? The term activator comes from the lone pairs on this oxygen are going to participate in the resonance system of these double bonds. Okay? So remember, if a molecule is aromatic, that means it has a fully conjugated system across the entire ring. Every carbon is sp2 and can participate in a resonated system. So these lone pairs are going to kickstart and activate or participate in the resonance system, therefore turning on the resonance system that's occurring within this ring. Now, looking at deactivators, Hno3 is a very great example of a strong deactivator, and we'll talk about different groups and how to recognize activators and deactivators in a little bit. But Hno3 is a strong deactivator. It's going to demand electrons to satisfy its positive charge. Because nitrogen lacks electrons, it's going to withdraw electrons from these double bonds. Therefore, it's going to unstabilize that aromatic ring, and it will no longer be participating in the resonance system. Okay, so therefore it deactivates that aromatic stability. Alright, so hopefully that made sense, and that you should keep that in mind to kind of get to know this unit instead of just purely memorizing. Alright, so this chunk right here is probably super important. I guess initially you might have to memorize, but eventually you should be able to do it without memorization. Alright, so within our activators and our deactivators, we have 3 different categories. We have strong activators, moderate activators, weak activators, weak deactivators, moderate deactivators, and strong deactivators. Okay? Now, these 4, strong activator, moderate activator, weak activator, and weak deactivator, are all under para and ortho. directors. Okay. Now the reason why a deactivator is a pair and ortho is because halogens are the exception to this rule. So regardless that halogens are electron withdrawing, it's going to direct it as para and ortho. However, moderate deactivators and strong deactivators are going to be still meta directors. Okay, so a strong activator is any group that has a direct lone pair attached to it, and it doesn't have any other group attached to it that will pull its attention away, such as moderate activators. So here you see lone pairs donating this way as well as this way. So this benzene ring is still getting activated, but not as much as these. Okay, so this is getting its undivided attention up here. This is getting its attention is divided. Alkyl groups are weak activators. So that means a methyl, ethyl, propyl, butyl. Now the reason I ordered it in this way is because when we have multiple substituents, let's say we have a methyl and a propyl, the propyl is going to dictate rather than the methyl. Okay, and we'll talk about what it means when we have two different substituents. Alright, we already talked about halogens. Again, I'll talk about why I ranked it in this way. Moderate deactivators, it's all of your carbonyls, ketone, ester, aldehyde. We have a cyanide here, as well as strong deactivators. These are the worst ones because they demand a lot of electrons. Okay, Hno3 is the most famous one. CF3, lots of inductive effect, and any NH3 or NR3. If a nitrogen has 4 bonds, it's going to contain a positive charge because it lacks that extra 5th valence electron. That's why it's going to demand electrons from this ring to satisfy itself. Alright? So I would keep this chart in mind, and I also drew this arrow because I'll explain in a little while. So if you want a cleaner version, here's an image I found on Google, but I would recommend either referring back to this chart or maybe memorizing it already in your head before the exam next week. Alright, so there are 2 rules for directors, okay? So this is what happens when we have 2 different groups, okay? So let's say I have an activator and a deactivator, such as OH and Hno3, okay? If I have both of these groups, if I add a 3rd substituent, now it doesn't matter what substituent I add. This does not matter if it's activator or deactivator here, okay? Does not matter. That's why I drew a smiley face to showcase that don't pay attention to if it's a withdrawing or donating. All that matters is what's already pre-existing on this benzene ring, okay? So OH is a strong activator, and I don't know why this is here. And Hno3 is a strong deactivator. Now when I have an activator and I have a deactivator, my activator takes priority, which means I am going to add my 3rd substituent, para-ortho, to my activator. So OH para is right across from it, so my smiley face goes over here. Alright, so that's the first rule. Now let's say I have 2 activators or 2 deactivators. So let's look at this example here. I have a ethyl here and I have a methyl. Now my ethyl it has more donating carbons and electron cloud to push it to make it more beneficial than this single methyl CH3. That's why when I'm trying to add my third substituent, again a smiley face, I'm going to add it para to my ethyl group, which is why it exists here. Now let's say I have a ester as well as another ester. Now the reason why I gave this example is because I wanted to showcase that regardless of the ester and amide, they could be flipped where the carbonyl is directly attached to the ring and where the oxygen or the nitrogen is directly attached to the ring. Now depending on how it's attached depends on if it's an activator or a deactivator. If it's the carbonyl, it's going to be the deactivator because remember carbonyls have a partial positive here and a partial negative here. So that carbon is currently lacking a little bit of electrons due to that dipole movement of that carbonyl. However, if it's directly attached on the O side, I'm going to have lone pairs to kickstart this resonance system and activate it. Okay, so be very careful on your esters and amides because you could have two different things. Now again, if I was trying to add a third substituent, this is my activator, so it's going to go para, which is in this position, to my activator. Alright, so here's a few more examples. I have two deactivators. I have a halogen, in this case I have a bromine, and then I have Hno3. So strong deactivator for Hno3, weak deactivator for bromine. Weak deactivator is higher up on this list. That's why it goes this way, as well as going this way. Okay? So whatever's higher up takes priority. So in this case, weak deactivator is better than strong deactivator. So it's going to go para ortho to my bromine, which is why I added my substituent right here. Okay? Now let's say I have two halogens. Again, just like with two alkyl groups, it matters which one is a better activator. Now chlorine and bromine, they are both halogens, but bromine has the bigger size, which is why it is going to have a stronger effect, and it's also because bromine is less electronegative. So this is less electronegative compared to chlorine. So bromine is less electronegative, that means it's a less electron withdrawing group, that means it's more of a donating group compared to chlorine, which is why bromine is going to be more favorable and it's going to direct where the smiley face is going to attach onto this ring. Okay, so which is why, remember, halogens are the exception to the withdrawing rule, or sorry, the deactivating rule. So it's going to be para to my bromine. Okay, so a question you guys might have is, all of my para ortho groups, so strong activator, moderate activator, weak deactivator. If I add another substituent, should I add para ortho or just para, or both of the orthos, or whatever? Okay, now if para is unoccupied by a substituent, you will attach it where para is located, right directly across from your substituent. Okay, now if para is already occupied by some other substituent, then you're going to go only attach to one of the ortho positions, not both. Either or, it doesn't matter which side. Well, it kind of does because you want to put it sterically favorable, so you don't want it to cluster up on your ring. Alright? Alright, so let's get back to it. Alright, so here I just do one more example where I use actual substituents instead of a smiley face to see what would happen if I add a fourth substituent. Okay, so here we have a strong activator, NH2, and it's strong because it has a negative charge. Sorry, a lone pair, which is essentially a negative charge. NO2 does not have a lone pair, but it has a positive charge, so that's bad. That negative charge or lone pair can donate into this, and this will pull away. That's why this is strong. That's strong activator. This is strong deactivator. So Br2 FeBr3 is going to add a bromine para to my activator, and I see para is unoccupied, so it's going to go slot in right over there. Okay, now I have three substituents. I have a strong activator, strong deactivator, and a weak deactivator. Okay, out of these three, strong activator takes priority. So if I wanted to add a chlorine, which is Cl2, AlCl3, my para is occupied, para to my NH2. This ortho is occupied, ortho to my NH2. So the other ortho position to my NH2 is where chlorine is going to attach. Alright, so hopefully those 4 or 5 examples kind of gave you an idea on where to put it. You know, this unit, this chapter rather, order definitely matters, and knowing whether something is activating or deactivating, and knowing the 2 rules for directors is crucial to getting your substituents in the right spot. Okay, so here's a screenshot of everything. If you guys want to pause the video or take a screenshot, and then here's all of this. Again, if you want to pause the video or take a screenshot. Alright, now we're going to move on to the next section, which is electrophilic aromatic substitution. Okay, so let's get started. We have about 16 reactions to get through. Alright, so we're going to use this benzene ring as an example. Don't disregard vinylic radical for now. So if I wanted to add a bromine, Cl2, or I2, I need these specific solvents to stabilize this position on a benzene ring to add on a halogen. Now I need those those solvents, because if you remember from OChem 1, exam 2, Br2 HB is a bad, it's a free radical halogenation, right? But if I try to add a radical on any of these carbons, you'll notice that all of these are vinylic radicals. So they're secondary vinylic. If you guys don't remember, vinylic is very unstable. It is not going to form that bromine radical. Okay, so that's why we need FeBr3, AlCl3, and Hno3 to stabilize that intermediate. Okay, and Br2, so Br2 will only react if I have something like this. Okay, or not even that, if I just have that. So I'm going to add a radical right here. This is primary benzylic. Okay, now my radical bromine can attach. Alright, so those are the first set. The second set are called Friedel-Crafts. Now there's 2 different types, alkylation and acylation. Alkylation has rearrangement, okay, and I'll talk about why it's rearranging. And remember, keep in mind, alkyl group is just any methyl, ethyl, propyl, or butyl. Okay. Now, all of these, we're going to use chlorine. Anytime you have chlorine, we're going to have AlCl3. Okay. And then I number these to showcase when the leaving group leaves, we form a positive charge here. It's on a primary positive charge, so it's going to attach just how it's seen. But as we know from Chem 1, Exam 2, positive charges prefer to be on secondary. So that's why I did a hydride shift right here. Again, Chem 2 or Chem 1, Exam 2 concept, where you can shift to make it more favorable for the carbocation, and then the carbocation is going to attach right here. So this is a isopropyl rather than an N-propyl. Okay. So really, you'll get a mixture of products where this is the major. So it'll be like, I don't know, 60%, 40%. Okay. So if you ever want to get this, the first product, you have to undergo Friedel-Crafts acylation. Now, acyl group, that's a carbonyl with carbon groups right next to it. So again, we're using a acid chloride, and anytime we have chlorine, we have to use AlCl3. So chlorine group leaves, you get a positive charge here. That positive charge interacts with this carbon. So we get this group. Now we have a carbonyl with 3 carbons. Now if I want to go from here to here, we undergo a reduction called Clemenson. Hopefully this is familiar to you. We have to use zinc hydrochloric acid to reduce that carbonyl to a plain alkane. Okay, so if our end goal is to go from a benzene ring to this structure, we have to do Friedel-Crafts acylation, get our ketone, and then reduce it using zinc hydrochloric acid, giving you a result of this product. Alright, so that would be reaction number 2 and reaction number 3. Reaction number 4 is called nitration, and it's exactly how it sounds. We are nitrating our benzene ring using HNO3 as well as H2so4. Alright, so that should be NO2 added. Now, if we want to reduce NO2 to NH2, we again have to use Clemenson, alright, which is again zinc hydrochloric acid. Now, we're going to skip ahead a little bit, and I'll show you a different way to reduce NO2 to NH2. It's called hydration, and you guys have seen this before. Use H2, and then you can use any of the 3, PD, PT, or nickel. Alright. Reaction number 5. We're just adding a methyl group to our benzene ring. There's no rearrangement because when this chlorine group leaves, our positive charge is on a methyl. There's no opportunity for it to rearrange on a more favorable carbocation. Yeah, methyl group is not the best stable position, but it does not have a choice in this matter. And again, anytime we have a chlorine group, we have AlCl3, so we have a methyl. Sulfonation is adding a SO3H group, and we do this using SO3 and H2so4. So that's reaction number 6. Reaction number 7 was our hydration. So let's go on to reaction number 8. Probably a segue to the most important ones. Alright, so reaction number 8 is formation of our disonium salt. So we're actually going to start from a benzene ring with NH2 already added on. That NH2 can be transformed into disonium salt, which is N triple bonded N, or N2. And this is done using NaNO2 and HCl. Okay? So this reaction is very important because the next step, it could be transformed into many things. So disonium salt can be turn into any number of these. Okay, let's run through them. So the first reaction, number 9, is hydrolysis. Using water and sulfuric acid, this can be turned into alcohol. Remember, anytime water is involved, there's a good chance that it's going to be some type of alcohol in my product. Okay, if I want to turn it into a straight up fluorine or iodine, I've used HBF4 or Ki, potassium I. They don't have a fancy name. Sandmeyer is all of the ones with copper, so CuCl, I get chlorine, Cu bromine, I get bromine, Cu cyanide, I get cyanide. Okay. Now, if you notice, iodine, chlorine, and bromine could have been turned just using our first reactions all the way up here. However, there could be a situation where you have to go from NH2 to a iodine, chlorine, or bromine. Okay, so you have to be very flexible, and you have to be aware of all your reagents, this unit, because there's going to be a lot of synthesis and reaction map, and possibly NMR, where you have to know how to go from one compound to another compound. Sorry, one structure to another structure. All right. So number 11 was Sandmeyer. Now, if I want to go from an N2 to just a plain old benzene ring, so a complete reduction is number 12, I have to use H3PO4. All right. So there could be situations where they give you NH2 to begin with, and then you have to form N2 or NO2 or SO3H or a methyl, you know? So if you ever just want a clean slate, go from a disonium salt, which is N2, and use H3PO4 to go to a plain old benzene ring. Alright? Alright, we're almost done. So number 13 is hydrogen deuterium exchange. That's exactly how it sounds. D2O, H2so4. All of these hydrogens are going to be replaced by deuterium. Now keep in mind, deuterium is hydrogen. It's a hydrogen isotope, but just at a heavier mass. Okay. Number 14, Wolff-Kishner. Again, something familiar. Wolff-Kishner is also a reduction. Now I have a carbonyl and NO2. Now I put both of these to showcase that it will only reduce the carbonyl, and it's going to leave the NO2, it's going to leave it and not do anything to it. Alright, so I have a couple of synthesis problems that I want you guys to try. I'm going to pause the video real quick and let you guys try it. Alright, so here are the 4 different synthesis that I want you guys to try. So go ahead and pause the video and then see how you do. Alright, so let's get started with the first one. I see that I have chlorine AlCl3, so it's either some type of Friedel-Crafts, and I believe it should be alkylation because I don't have a acyl group. So I drew my chlorine leaving, and then I have a positive charge here, and then I drew this second positive charge because it does not matter if I have a primary positive charge here or if I have a primary charge here. So no rearrangement necessary. So it's going to attach on right here. And the reason why we want to do this step first is because we want to have NO2 directly para to our ethyl group. Okay, which brings us to our next reagent, Hno3 H2so4. Now that the para is occupied, this is still in charge because this is still our activating group, and this is our deactivating group. Br2 is going to come in and attach right here because it's the ortho position that's still available for this ring to attack. Alright, so next one It's kind of long. It has 7 steps. Hopefully, if you're able to do this, you're able to do your exam. If not, I apologize. Alright, so again, same step. We form a ethyl in the beginning. Then we do sulfonation to get SO3H pair to this. Then now that our pair is occupied, we can add Hno3 to our ortho to our ethyl. Now that we have Hno3, we can reduce it to get NH2, which I didn't draw it, but NH2 will be turned into NaNO2. Remember, NH2 undergoing this reaction will form our disonium salt. Now that disonium salt can be turned into OH, but so using H2so4 water, okay? And then lastly, if you guys notice that there's a bromine here, and you're probably thinking, maybe I should do Br2, FeBr3, and you will be wrong, and you'll get it wrong on the test. So, which is why you're not going to make that mistake, because you'll know that that can only happen if you use Br2 and light. Remember, at the beginning of this page, I talked about how this is from OChem 1, exam 2. It's a free radical halogenation, secondary benzylic, that is the most stable radical position, and not one of these benzylic secondary vinylic position. Alright? Let's go to our third one. I'm not sure if this is harder. Hopefully it should be easier. Alright, so now we have a ethyl here, and we want to get a chlorine here. Okay, so how do we get two groups meta to each other? Now you might be thinking meta, electron withdrawing group, but chlorine is a electron withdrawing group, but it's the exception, so it's going to be para-ortho, and our ethyl group is not para-ortho to this. So that means this had to be some type of carbonyl that got removed after we added on the chlorine, which is exactly what happened. So we did Friedel-Crafts acylation. We added on a acid chloride. Acid chloride means solvent is AlCl3. This is our first step. Second step is to add our chlorine, because this is a deactivating group, which forces any second substituent to be in the meta position. So one of these positions. Now that we have our chlorine group added in the meta position, we need to get rid of that carbonyl. We don't like it. We want it out of here. And we're going to use it using a great reducer. Zinc HCl is a great trusty reducer. So it's going to get you this end result. Now I drew this chlorine because we would not have to go through all this stress. We would, if, what I meant to say is, if chlorine was here, steps 2 and 3 would actually be flipped, because we would want this to be activating before we add our chlorine group. Okay? Hopefully it's starting to click. Hopefully you're starting to see why order matters, and not only in the sense of PEMDAS. Order matters for chemistry also. Alright, lastly, this is actually kind of probably the longest one. So I drew the end result, but our starting again is just a basic benzene ring. So what we want to do is start with a methyl group. Okay. Now this methyl group can also be an ethyl, propyl, butyl, doesn't matter. As long as we have some type of alkyl group, okay, and you'll understand why. So after we have our methyl group, we're gonna introduce SO3H. It's gonna go para. After we have that, we're gonna add Hno2, which is gonna go ortho to our activating group. SO3H, I believe, is a deactivating group, but I have to double check on that. So yeah, methyl group takes priority. After we have that, we're going to reduce NO2 to NH2 using Clemenson. And then after that, we're going to turn it into disonium salt. And after that, we're going to remove SO3H. What? How do you remove SO3H? You can remove it using sulfuric acid. Now this is actually number 15, reaction I haven't told you about. So I apologize for that, but it is what it is. So after that, you can turn methyl group into a carboxylic acid using Hno3 NaOH and heat. Again, this is another reaction I didn't tell you about, but this is what you should be getting. Okay, so it has 7 steps. Step number 6 and 7 are unique, but hopefully it still makes sense. So you have to introduce SO3H to force NO2 to go on the ortho position, and then after you do all your reactions, then you remove your SO3H and then you oxidize your methyl group. Okay. Now Hno3, I actually realized this in the second part of chapter 17, but I'm gonna go ahead and introduce it now. So Hno3 is a strong oxidizer. If you guys remember from last unit, it's gonna turn any methyl or ethyl or any long chain into carboxylic acid. Now the reason why this isopropyl does not turn into carboxylic acid is because it needs a primary or secondary alcohol to be later turned into carboxylic acid. Okay? Now you might be thinking, oh wait, secondary, I thought that will turn it into a ketone. That's correct, but a ketone can then later be further oxidized into a carboxylic acid. And if you notice, this tertiary alcohol will remain as a tertiary alcohol. Now I can't remember if it adds on the OH or if it leaves it as isopropyl, but for the most part, this should be right. Alright, so well, there you have it. Let me zoom out a little bit so you can see all of them. So here's the very last one, and then here's the rest of those. And I'll slowly scroll up. If you guys need to take a screenshot, pause the video or whatever. Alright, and then let me go to this one again. Hopefully you guys got this. So your reactions are important, but your reactions won't be anything without your directing roles. So you can think of your reactions as words or like a foreign language, and all of this stuff, all of the directing roles can be like a translator to make sense of what you're doing and to actually put it in the right place. Okay, so this whole unit is all about, putting in the right place, and order matters. Okay, if you learned anything from this video, it's that order matters. Okay, all right. So I'll see you guys next week for the last video before your exam. It's going to be about the rest of chapter 17 reactions. It's going to be nucleophilic addition, aromatic addition. And there's not too many, and I'll also talk about basicity of amines. But if you guys haven't, and if you guys want to learn about basicity of amines, go ahead and check out Brandon's video. It should be on the same area. He has a quick 10-minute video on how to rank by a great example of basicity of amines, because that's a very high likely chance of showing up on your test. Okay? Alright, until next time.